Hi everyone, Dr. P here, and in this lecture we're going to take a look at another two concepts that are important with Lewis structures, and those are resonance and formal charge. All right, so what is resonance? Well, to see an example of resonance, let's take a look at the nitrate ion, NO3 minus, and let's draw the Lewis structure. So for our valence electrons, we have nitrogen, which gives us 5. We have 3 oxygens, which gives us 3 times 6 is 18. And then we have the negative charge, which gives us 1. So that's a total of 24 valence electrons. So let's go ahead and put our nitrogen in the middle and put our 3 oxygens around it. Now I can start filling in my lone pairs, and I might be tempted to just put 3 lone pairs around each oxygen. That would give me 2, 4, 6, 8. 2, 4, 6, 8, 2, 4, 6, 8. I have 24 electrons, but I'd only have 6 in the nitrogen valence shell, so it would have an incomplete octet. So I'm going to put a double bond here. Okay, and that's going to give me then 2 lone pairs. So I've got 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. And now I've got 1, 2, 3, 4, 5, 6, 7, 8 valence electrons around nitrogen. So that's good. Okay. But, so I'll put this in some brackets here and we'll give this a negative charge. But what if I did this instead? Or what if I did this? Okay, these guys, I'll put them overall in brackets here. These Lewis structures are all equivalent. They're all equally valid. And the only difference is the location of the bonds, the location of the electrons. We have the same atom in the middle, nitrogen. We have 3 oxygens attached to that central nitrogen. The only thing we've moved is electrons. In fact, I could draw in some arrows to show how these electrons move. And let me do this in blue, I think. So, I could push these electrons there, and then I have to push those guys up there, and then I'd get this. Or I could push those electrons there and push those ones up there, and I'd get my third structure. So in this case, equals 2 electrons. So a pair of electrons is my arrow. All right. And so what we have here are called resonance structures. So resonance structures are additional valid Lewis structures. For a particular atom or ion. And they only differ in the arrangement of electrons. And so those could be lone pairs, they could be bonds, but the only thing we do is we push around the electrons. Now I know this guy looks like this guy rotated and rotated again, but for resonance structures, we're going to pretend that our atoms are stuck to the paper and we can't rotate the molecule. We can just push electrons around. And it turns out that this is a more accurate picture. In reality, what we have is a nitrogen with 3 oxygens bonded to it. And then the electrons are somehow distributed. This isn't quite accurate, the negative charge here. So all of the NO bonds are equal length. Okay, typically double bonds are shorter than single bonds because they are stronger. And so a double bond here, we'd expect that to be shorter and these guys to be longer single bonds. But in reality, all of the bonds are the same length. So they're all kind of like a bond and 1/3. So they're all like a bond and a third instead of being a single or a double. They're in between. And so resonance structures are a way of getting around some of the limitations of Lewis structures to depict something that's more accurate. In reality, reality is an average of the resonance structures. So if we blended all these 3 together, we get a better picture of what things really look like. Okay. Now we need this concept of resonance in order to compensate for the fact that we are localizing our electrons. That's our big assumption in the localized electron model. All right. Now, the one thing you may have noticed is that, and maybe before I talk about one thing you may have noticed, let me just underline resonance structures and the definition here. One thing you may have noticed is I have an overall negative charge. Now, given that oxygen is more electronegative than nitrogen, you might expect more negative charge on the oxygens and less on the nitrogen, and that is in fact what we see. And so that gets into the topic of, or the concept of, formal charge. So formal charge is, it's kind of like oxidation states or oxidation numbers. It's a way of assigning electrons arbitrarily to atoms in a molecule. And we can also define it as the difference between the number of valence electrons on the free atom and the number of valence electrons that we assign to it. And our valence electrons assigned equals our number of lone pairs, LP, electrons, plus half the number of shared electrons. Okay, so what does that look like? Well, let's look at NO3 again. So I have nitrogen, I have oxygen, 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 and put in my lone pairs. Now I'm not going to put this in brackets right now because I'm not showing the overall negative charge, but rather what I'm going to show is formal charges. So I'll start down here because this oxygen has 0 formal charge. And I know that because it has 1, 2, 3, 4, 5, 6 electrons assigned to it. Each bond counts as 1 electron. The bond is split in terms of assigning the 2 electrons. Each atom gets 1. So I have 1, 2, 3, 4, 5, 6, and normally I have 6 valence electrons. So no formal charge. We don't write anything. What about this oxygen? Well, I have 1, 2, 3, 4, 5, 6, 7. And so normally I would have 6, so I have 1 extra electron. So that's a minus formal charge. So I'll put a minus sign there. And same for this guy here. That has a minus sign. And then the nitrogen in the middle has 1, 2, 3, 4. Let me get my hand out of the way. It has 1, 2, 3, 4. So normally nitrogen has 5, so I'm 1 short, so that would be a positive charge. So just to go over it again, this oxygen has 1, 2, 3, 4, 5, 6, and it should have 6, so that's 0. These oxygens have 1, 2, 3, 4, 5, 6, 7. They should have 6, that's an extra, so minus charge. And then the nitrogen in the middle has 1, 2, 3, 4, and it should have 5, so it's 1 short, so that's a positive charge. And then we can go ahead and draw our resonance structures as before. But with adding in the charges. All right. Now, why do we bother with formal charges? Well, formal charges can help us determine how good a Lewis structure is. So let's look at another example. Let's look at the sulfate ion. So I'm going to have, let's see, my valence electrons. I have sulfur is 6, 4 times oxygen, 4 times 6 is 24, and then my negative charge is 2 electrons, so that's 2, so that's a total of 32. So one thing I could do is do this. And put my electrons around here. So now in this case, each oxygen has 1, 2, 3, 4, 5, 6, 7 electrons assigned to it. Normally it should have 6, 1 extra electron, so that's a minus sign. Same there, same there, same there. And now the central sulfur has 1, 2, 3, 4 electrons assigned to it. It should have 6, so it's 2 short. So we're going to have a 2 plus charge on that central sulfur. Okay, let's compare this to, what if we did this instead? What if we did sulfur and these are actually resonance structures. So what I'm going to do here is I'm going to push these electrons down there and push those electrons there, and I'm going to have the following. Whoopsie, too many electrons around that guy. Sorry about that. So now I have two oxygens that have 1, 2, 3, 4, 5, 6, 7 electrons. So those are negative formal charge. And I have two oxygens that have 1, 2, 3, 4, 5, 6 electrons. So those are 0 formal charge. And then my central sulfur has 1, 2, 3, 4, 5, 6 valence electrons. So it has 0 formal charge. I'm just going to write etc. here because it turns out that there are a total of 6 resonance structures that have 2 double bonds between sulfur and oxygen and the sulfate ion. So now the question is, which is a better Lewis structure? We have more formal charge, but it obeys octet rule. Here we have less formal charge, but it exceeds the octet rule. Well, in reality, what we have is we have something that's in between these, where we have the same sulfur-oxygen bond length for all of the sulfur-oxygen bonds, but it's not quite a single bond. It's not a double bond, it's probably like a bond and a half. And most of the negative charge is out on the oxygens with some positive charge in the middle. So we actually have a blend of all of these. And this is something that you have to sort of weigh. Okay, obeying the octet rule is good. I'll give that a green check. Less formal charge is good. I'll give that a green check. And then not obeying the octet rule. I can't seem to find my red pen. So I'm going to have to, well, we'll do it in orange instead of red. Not obeying the octet rule is not good. So maybe we'll put an X there. But more formal charge is also not good. So in general, atoms and molecules try to achieve formal charges as close to 0 as possible. So we're going to try to minimize formal charge. So we will try to minimize formal charge. And then if we have to have negative formal charges, then they're going to be on the more electronegative atoms. Apologize for the squeaking that my writing is making here. There we go. So we can sum up that way. So these two concepts of resonance and formal charge help Lewis structures do a better job of explaining the structures of molecules and also how molecules react. And you'll look at this in more detail in future chemistry courses, some in 1B and then an awful lot in organic chemistry, 12A and 12B. All right, so that was resonance structures and formal charge, and these excuse me, should help you with drawing good Lewis structures. In the next videos, we'll take a look at the shapes of molecules based on what kind of bonding we have going on, and that'll wrap things up. All right, well, until then, stay safe out there. Bye now.